Okay, welcome back, everybody. Today I'm going to do a little presentation about circuits and resistors in circuits and the various ways we can configure those resistors and how we can track and determine how the voltage and the current gets split up and used amongst those various resistors. And then at the very end, the last couple slides, I'll talk about Kirchhoff's rules, which are the formal application of conservation laws to circuits. And then the last slide will be all the formulas that you need to numerically solve for things. So let's start with just a simple circuit, right? Why does the circuit need to be complete, and how do the charges move around in it? So what you see here is an animation where you have these, frankly, imaginary positive charges, right? But that's how we define current. Going around, and they have to go in a complete path, and you can see that, right, for every no charge can move without the charge in front of it and behind it moving, hence the need for a complete path, right? And if we were to open the path anywhere, all this charge flow would stop all at once. And so what you see on the left here is some place where the charges are gaining energy, right? So that's the job of the battery. And then there's another place where the charges are giving up their energy, and that's the resistors in our circuit diagrams, right? It could be a motor, it could be a light bulb or something like that. Resistors take that electrical energy and just basically turn it into heat, right? If you think about a toaster oven or something like that, the big red glowing coils there are just giant resistors. All right, and so embedded in here are the wires, right? The pathways that are conducting all these charges. So here's a picture of what that would be, right? That animation was showing you, like, the battery had that job of lifting the energy of the charges, and then the charges deposited their energy here, and then they went back. So here's a formal circuit diagram on the left, right? So we have the symbol for a battery, a DC power supply, one short and long parallel line. You don't always see the plus and minus signs. In fact, you rarely see both. And frequently they won't put either. You're just supposed to know the longer side is positive and the shorter side is the negative. And since we think about current as being the flow of positive charge, the current comes out of that side of the battery, flows through these wires, deposits its energy, loses voltage on this resistor, and then comes back home, right? And so that's what you see in the animation. So the height here is how we're demonstrating the voltage, right? And this is a common analogy, right? Because we know about gravitational potential energy, you lift things to higher ground and they have more gravitational potential energy, and lifting things to higher voltage, positive charges specifically to higher voltages, gives them more energy. And so that's why this is a really good metaphor for simple circuits. Now, what happens if we put two resistors in series, right? Well, there's only so much energy we've given. The battery only has so many volts to give each charge, right? So many joules per coulomb is the voltage. And then by the time you complete the loop, if you're a charge, you will come back down. You only have this potential difference to use over the whole course of the circuit, and so you will use the entire voltage over the course of the circuit. So some of it needs to get used on the first resistor, and then the remainder on the second, because if you think about the difference between the height over here on this side of the circuit diagram where the energy is being used up, that is the same height, right? It's defined. The height is given to it by the voltage. So there just is no other way for it to be. And then the values of the resistors determine how that voltage will be split up, right? A 30 ohm resistor is 3 times harder to get through than a 10 ohm resistor. So if you look at this, you're roughly using 3 times the height here, 3 times the energy gets deposited there as it does in the 10 ohm resistor. And so this is the basic way to conceptualize resistors in series. And you get a couple of the rules here already, right? The voltages have to add up to the voltage of the battery. You should have already seen that in one of the previous labs. And the current has to be the same, right? Because so for every charge that enters that resistor, another one has to leave, has to enter, that one has to leave. And so things that are in series have the same current. Right? So here's a formal circuit diagram for the picture that we have over here, right? And so I'm looking at the circuit diagram, and I'm thinking about charges coming in, positive charges coming in, being raised